All right, let's get started. Good morning, everyone. Um, I'm sorry we have to do this remotely, but I hope you all found the link in time. For your information, the lecture will be recorded, and once I have the recordings, I'll be happy to share the link on Quercus. But I would still encourage you to take notes, and I will also make my present the notes I take on Quercus, so you will be able to download this as well. So we are still in this chapter of the covalent bonding, and I'd like to continue now where we have left off, unless there are some more questions regarding the material we've covered. So if you have questions, please raise your hand in Zoom, and you can also just unmute yourself and interrupt me. We did discuss this idea that your bond looks something like this, where you have a nucleus with a certain nuclear charge Z and another nucleus with another nuclear charge Z, so Z1 and Z2. And then your electrons will arrange in an electron density, which results from the addition of the molecular orbital solutions phi for every state that is occupied with electrons. And these wave functions can have positive and negative signs. And so we take their probability densities, because we know that the electron density is an observable, which has to be positive and real. Now, there is the question then, as you walk through chemical compound space, meaning you're changing your nuclei to some other combination, maybe at a different distance. So suppose my Z1 now becomes, for a new compound, Z1 prime, and here I have now a Z2 prime, and again some electron density, and this is some real space axes I call X, aligned with the molecular axis. And this is a rather realistic picture of how a diatomic molecule could look like. Question is, of course, as you go from this one molecule to another, is there something we can learn, something we can predict? What are the trends as you vary in composition and structure? Now, there is something introduced by Langmuir in 1919, who observed that isoelectronic that means these are electron number conserving systems often exhibit similar properties. That means without regard to chemical composition or bond lengths, systems can have similar properties. And just as an example, let's consider two pairs of isoelectronic compounds, namely the CO molecule and the N2 molecule, as well as the CO2 molecule and the N2O molecule. Now, these two pairs of compounds are isoelectronic. So maybe for CO2, you know the Lewis structure formula. If you change one oxygen to nitrogen, and at the same time this carbon to nitrogen as well, you have not introduced a formal total charge, and you could draw Lewis structure formula like this, where the formal charges would be like that. Okay. So these are two isoelectronic molecules. And now let's consider some properties. In particular, we'd like to look at the melting point in Kelvin, or the boiling point in Kelvin. Also, the electron the normal density, the mass density, gram per centimeter cube. We will also look at the solubility in water, as well as maybe the bond strength, so which is the atomization energy, right? So for carbon monoxide, we have some experimental numbers here we can enter. So this is on the order of 68 Kelvin. For N2, the melting point is at 63 Kelvin. So similar. Now you add another atom and your melting point goes up to 217 for CO2. And not exactly the same, but still in the vicinity is N2O with 180 Kelvin. So the boiling point for CO is at 82. Why it evaporates as dry ice, right? And for N2, the boiling point is 77. So when you need liquid nitrogen, you have to cool things down and below 77 Kelvin. The corresponding boiling points for CO2 are at 195 and 184 Kelvin for N2O. So again, very similar numbers. The density for CO is 0.8, and for N2 is also 0.8. For N2O, for CO2 is 1.03, while for N2O is 0.99. So very similar numbers. Yes, there's a question, please.
Yeah, why is the melting point for CO2 higher than the boiling point?
That's a good question. I'm wondering too. Let me look into those numbers. I have to. Maybe I copied them wrong, but yeah. So that's surprising indeed. I wouldn't expect that either. It's not really possible. So let me check on these numbers later, please. On the solubility in H2O, we have 0.03 for CO and 0.02 for N2. And for CO2, we have 1.7 and 1.3. So you see overall, there's usually within a couple of percentage points, you will have similar properties for isoelectronic systems, especially if they have the same number of atoms. Now, in terms of bond strength, there's only one bond in the diatomics, so I only have this for the diatomics. You will, in kilojoules per mole, you will get more than 1,000 for CO and 940 for N2. Now, again, rather similar in terms of percentages. If you compare this, though, to another isoelectronic species, such as BF, this is in a series where you have N2, CO, and then BF. These are all isoelectronic, right? So your nuclear charge here is 7,7, 6, 8, and 5, 9. In BF, the bond length, the bond strength is only 640 kilojoules per mole. So that's quite a deviation, right? And it tells you that this rule of Langmuir is just an approximate rule, right? So let's maybe call this a rule which is approximate. So it's quite common in the chemical sciences that we have qualitatively rules of thumb, and you should not expect them to hold rigorously. So the explanation as to why BF might break that rule is that the nature of that covalent bond is quite different. If you consider the Lewis structure, boron has 3 electrons, and now fluorine is a halogen. It's your 7 valence electrons, and you will form this bond, right? So clearly this is a single bond as opposed to a double or triple bond, CO and N2. And also you do have some radical character here, which will not help with the stabilization of this bond. So this is single bond. We can rationalize this in hindsight, but of course not always clear before. I should also mention that there is another rule. It's called the isolobal principle. And it relies on this idea that we could make use of the shape of the atomic orbitals independent of where the element sits in the periodic table. And so if your valence electrons take a certain shape, then you might expect your system to behave in similar ways. So, for example, if you have a carbon which is sp4 hybridized, sp3 hybridized, and suppose it's in the methane molecule where these two last hydrogens are behind and before the plane of the board I'm using, then you could imagine what would happen if you detach one of the hydrogens. You would have a free sp3 orbital with just one electron sitting in there, right? Now you can encounter a similar situation, and that's this isolobal principle, that you say the properties of this system are similar to a metal atom that has some ligands. So, for instance, ligand 1, ligand 2, ligand 4, and a ligand 5. So this metal atom could be, for instance, encountered in a D7 electron configuration. And you would then have one orbital left with one electron exposed. And this isolobal principle tells you that the reactivity here would be similar. Even though these two elements are very far away from the periodic table, and in fact do not have the same number of electrons, but you see that the valence electrons, so the electronic configuration of the valence electrons determines the trends. Okay. So it does not necessarily mean that the bonding strength, for instance, is very similar, but you might be able to expect similar geometries, so similar reactivity, and again the trends to behave similarly, right? Meaning, if you took one of the ligands in the metal and you started to vary it and replace it by some other functional group X, and similarly in the carbon case, you take this one of the binding atoms and you substitute this also by some other group X, then you might expect similar trends in bonding strength of your open orbital. Okay. Yeah, and then I'd still like to mention, of course, so we've already alluded to this, but among covalent bonds, there is such a thing as the bond order. We can draw that in terms of valence electrons for the various hybridization states. That means if you consider, again, a methane kind of situation, you can you would have one electron here, and now you imagine another carbon with the same kind of configuration, and you can see that this is what we would depict as a single bond between these two carbons. Now, similarly, you can consider, so these are sp3 carbons. Similarly, you can consider sp2 carbons. They could look something like this, where you have your single bond again with the hydrogens in front and behind the board. So now I have for every carbon atom 3 valence electrons, and now the fourth valence electrons would sit in the p orbital of the carbons, and these p orbitals above and below the single bond would start overlapping and form what is known as our double bond, an ethylene. And this is ethane, ethylene. And these are carbons in sp2 hybridization. And then, of course, we have the triple bond when our carbon is in an arrangement where you only have 2 hydrogens in the molecule. Again, you have your double bond, which is now in the plane, but now you have a second p orbital, which comes out of the plane and behind the plane, and it stands orthogonally, perpendicular to the pi orbitals in the plane of your molecule, and in this arrangement, you then have the triple bond in acetylene. And these are so-called sp hybridized carbons, right? So you see, as you increase the number of electrons, in the bonding, you can vary the bond order, and this results in additional stabilization. So as one would expect, the atomization energy, the bonding strength, grows with the order. And again, I have some numbers to exemplify this. So if you consider your bond, the bond order, a certain molecule, and the binding energy, which is really the same as the atomization energy, again measured in kilojoules per mole. So for a single bond, that's bond order 1, and let's use as an example the chlorine molecule. That energy is 244 kilojoules per mole. We can go to a double bond with bond order 2. We take the O2 molecule, and this has a bond of roughly 500 kilojoules per mole. Then a triple bond you could encounter N2. That's the 950 you've seen before. And so you see with doubling, going from single to double, I can double my energy, and then going double, triple, I can even gain more than 50% of what's stored in the bond. Now this depends, of course, on the specific molecule, but it's not as if the trend necessarily should become sublinear in your order. Now, these bonding trends are not always obvious to accurately predict. And so, again, we have to make spectroscopic measurements of these, or combustion experiments to thermally measure the energy content, or we have to perform very accurate quantum mechanics calculations. So this is very difficult to predict by intuition accurately. But in terms of trends, it's quite easy. And we should note, however, that these covalent bonds with multiple orders, so higher bond orders, they typically occur only for the early, so second row elements, right? So second row main group elements. So only for the heavier elements, the distance which you see here among these carbon atoms here, this kind of distance increases because the atomic radius increases, right? And the directionality of your single bond imposes that. So there's no double bond without the single bond in between the atoms. And so if your atomic radius is larger, the perpendicular p orbitals, so these would be 3p, right? So for the third row in the periodic table, 3p or 4p element, these orbitals would be so far away from each other that this kind of pi-pi interaction which you have here is too weak to meaningfully contribute. So that's an explanation for this, and we also have this by quantum mechanics. You can show this example that if you take 2 times the energy of this molecule, where you basically simply go below nitrogen in the periodic table. And instead of looking at N2, you would look at P2 for phosphorus. If you look at 2 times the energy of this, you will find that the energy will be above the energy of a molecule that combines all 4 atoms, right? And this P4 actually a very intuitive structure where you would have simply a tetrahedron highly symmetric with a bond length of 2.25 angstrom. Right? Now this, drawing the lone pair electrons as well, this kind of, sorry. Okay. So this is exactly the other way around for 2 times the energy of N2, which would be much lower than the corresponding geometry for N4. Right? Now, this P4 compound is actually quite infamous. It's known as white phosphorus. Sorry. And it is sadly classified as a chemical weapon. So you should be very careful with this stuff. It ignites spontaneously. With oxygen. As soon as it's exposed to air, it will burst into flames. As soon as it encounters aqueous conditions, it forms phosphoric acid with water. And upon contact, it will burn through organic materials. And so if you are being attacked with this, you you will get skin burns, which are very severe. Apparently, they can even go through the bones. So this is a banned substance. Right? Now, this danger is because while this 2p here, the p2 system is so unstable it doesn't even exist. P4 is still quite unstable. That means highly reactive, and there is a safer structure. This is known as black phosphorus, and it's even roughly 40 kilojoules per mole lower than white phosphorus. Now, this black phosphorus is more stable, and it assumes an interesting 2D layered structure, where you would have a chain of phosphorus atoms in one level of the blackboard, and then in front of the blackboard you would have another chain with the same angle. So I'm drawing these bonds as thick bonds to illustrate that this chain is above the plane, and then again it reverts to the original plane. You have the next chain of phosphorus atoms. I hope this is clear. So this chain is above, and this chain is in the blackboard, and you keep on doing this and going lower and lower, and to the right and the left, and that forms a plane of phosphorus. And on top of that plane, you have the next plane, and so on. So you build a crystal out of these layers, right? So this is an example of a crystal you can form with covalent bonds, right? And this is quite analogous to so the first synthesis, I believe, was in 1914, and there's some to the layered materials which you encounter in graphene, which was only really discovered and established quite recently, and it got the Nobel Prize in 2010. And so one of the Nobel laureates for this is now a professor at the University of Singapore, and is involved in a collaboration with University of Toronto, for which we my lab just recently secured funding. So something that's very interesting to us. We have a question here. The structure, is it meant to be like a staircase or like an accordion? I believe the latter would be correct, right? So you have a bunch of a zigzag kind of structure in one plane, and then you go up a small step, right? And then you go down again. So indeed the accordion picture is more appropriate. Now you need that you cannot stay in the plane in all directions because of this hybridization in the elements with these single bonds, but this is can be overcome if you can make use of double bonds, right? Then you find planarity, and this tells you, in combination with what I said before, that only the early elements can have higher bond orders. This tells you why these early elements have such a rich chemical diversity, because basically they have more geometrical degrees of freedom. So planarity typically requires double bonds, at least double bonds, right? And just for example, remember our carboxy cases. So that's the carbonate, right? And we have the resonance structures, carbonic acid, which are all planar, right? So here you have 4 atoms, which will be perfectly planar. Or you consider the graphene case I mentioned before, where all atoms are in a plane. So you can see how the covalent bonding can impose very specific geometries, and this is really one of the key hallmarks of covalent bonding is the spatial arrangement, right? Spatially rigid arrangements are key features of covalent bonding. So this typically implies that the curvature of the binding potentials that is, when you look at the energy as a function of a distance, is rather high, okay? That also applies to angular distortions, right? So these are rather rigid geometries, which means these atoms are not like billiard balls that can rearrange in no matter which way, but you really have to overcome rather high barriers, energy barriers, to change from one geometry to the other. This has been formalized by what is known as the so-called valence shell electron pair repulsion, typically abbreviated as VSEPR, which specifies some rules that I would like to tell you about maybe after the break. Are there further questions so far? That doesn't seem to be the case. I would then like to suggest that we take a 15 minutes break and we resume at 1:15. Okay, there's a question. I'll address this question after the break, okay? Thank you. Okay, let's continue with the lecture. So I wanted to, hang on. Okay. One second. Okay. I wanted to tell you about the valence shell electron pair repulsion, the VSEPR rules. And the first rule states that you want to maximize the distance between the sigma and lone pair and pi electrons. Okay. And the second rule is that the lone pairs repel more than a sigma electrons. Right? So maximizing the distance between the sigma bonds results in the tetrahedral planar trigonal and linear geometries for single, double, and triple bonds. And the lone pair rule explains why, if you consider methane if you consider the angle in methane, it's 109 degrees between, so that's the carbon, the hydrogen-carbon-hydrogen angle. If I compare this to ammonia, they have a lone pair, this angle is now decreased to 107 degrees, implying that this lone pair has no bonding partner, right? So as opposed to methane, there's not an atom up here attracting the electrons. You're missing that. And so the electrons have to be closer to the nitrogen, and they occupy more space. And consequently, they repel the other single bonds more. And I can then also look at water, where I now have two lone pairs, and in this case, the angle is decreased further to 104 degrees. We have furthermore, so this is as you go horizontally in the periodic table. Furthermore, you could also go down vertically in the periodic table. And what you see is, if you now go from nitrogen to phosphorus, you have the same kind of valence electron configuration, but the lone pair electron is larger because it's in a higher principal quantum number, so it occupies more space, and correspondingly there's more repulsion, and your angle is further reduced to 93.5. And if I go further to arsen, we are at 92 degrees, and in antimony, you'd be at 91.5 degrees. Okay. So this VSEPR rule explains such trends, and it does this in a rather reliable way. So this also explains then why in the hybridization cases you would encounter planar geometries and linear for SP hybridization. So this explains for example, if you consider cumulines, these are arrangements where you have double bonds which are attached to each other. Each double bond has 2 electrons, right? So an example for this is the allene molecule, which has this kind of structure, and the 2 of the 4 hydrogens are above and below the surface, and 2 are in the surface. So one question is, if you form these covalent and higher order bonds like doublet and triple bonds, you also encounter the saturation with hydrogens. And while you do have crystals that can form, like graphene or diamond or the black phosphorus we mentioned before, in many cases you also form in the presence of hydrogen in particular. So if there's hydrogen, you often saturate to form molecules. And these are finite molecules. And these systems also condense. And they condense no longer due to covalent bonding, but due to van der Waals interactions. And we will still encounter them later on in this course. So generally speaking, compounds with covalent bonds, this should be in general, they are typically rather volatile. So think of all the molecules we encounter on a daily basis in terms of smell, odor, right? These are typically covalently bonded atoms, and this means their melting point and their boiling point is rather small or low, right? The exception of this that they are large in size. So we do not easily evaporate entire proteins, or entire polymers, or that they contain polarized bonds. So this means that while inside the molecule you might have polarized covalent bonds, the van der Waals interactions are becoming ionic, and that interaction strength is so large, as you will see later on in the subsequent chapters. That interaction is so strong that it impacts the volatility dramatically. So, for instance, if you consider salts of organic acids, these are obviously very crystalline and not at all volatile. But these are the exceptions. So for very strongly polarized bonds, now they are usually also soluble in one solvent or another. They tend to be soft. If you have a crystalline made of a crystal made of molecules, and the van der Waals interactions are so soft and not directional that they that on the macroscopic level these are not hard material. Again, the exception can be diamond, right, which has really a very strong hardness, but that's a regular periodic crystal, and it's not dominated by van der Waals interactions. They are also typically transparent to light, meaning the electrons are so deep in the potential that their excitation would require frequencies higher than what we have in the visual light spectrum. They are typically colorless and insulators. So all these are related to each other to where the electrons sit in the potential. I should also remark on the softness. I forgot to explain this. There was a question before the break regarding the curvature. What I would mean. So the curvature is if you have a binding potential like this, right, where this is your binding energy, and this is the energy, this is your zero energy, this is the distance. The curvature of something like that would be the second order derivative with respect to the distance, right? And that's the curvature of such binding potentials. And if you have a very shallow binding potential, right, or a very stiff one, their difference, as you can see here, they have the same interatomic distance, the same binding energy, but they change in curvature, right? So curvature that corresponds also to the stiffness of the bonds. And these covalent bonds are very stiff and directional. All right. Are there further questions on the covalent bonds? I don't see any, and so I would like to still use the remainder of today's lecture to enter the next subchapter, which is subchapter 3.2 on the metallic bonding. And to really appreciate what a metallic bond is, I'd like to do two drawings, which are actually the first drawing relates to what we just discussed, the covalent bond. And we'd like to look at the covalent bond in terms of the energy spectrum, which would result from solving the electronic Schrödinger equations for these early elements that exhibit covalent bonding. So let's consider this, where we have energetic eigenvalues here, or actually, let me erase this. We will have multiple properties on this axis. Let's just say this is 0, and we draw an atomic potential of an early element, which is fairly narrow. So this is Z over the distance, right? And this could be this distance. Let's call this X. Right? And this is the external potential of that atom, right? This is the position of the atom, right? And let's suppose this is the nuclear charge again, and these are its electrons, right? Now, what are the eigenvalues of these electrons, right? They are fairly low lying, right? And you have very few. Right? It's an early element, so there are not many electrons. So this would be maybe the picture for lithium, for example. Right? This is the electron density of lithium. And now there are more states above which are empty, and their energy distance. So these are the eigenvalues. Okay. And their difference decays with 1 over n squared. Right? So the higher the quantum number, sorry, now I used I, let me put n here. The higher the quantum number, the quadratically smaller the difference in eigenvalue, right? And now, as you go out here, right, your spectrum will become denser and denser. And once you pass the zero, you're entering the conduction band where electrons would be free to travel and conduct electricity. So we are very, very far away from this. And this is the covalent picture, right, in a lithium atom, right? So an early element. Now we go to a metallic element. So before we do that, let me just summarize. So there are few bonding states and valence electrons. In a rather stiff potential. So this holds for all early elements, and this, because the electrons are so low, it implies the large ionization potentials and the properties I mentioned at the end of the last chapters with the strong insulator, right? So you're far away from this level where your electrons become conducting. And so the only way you can lower the energy further for these electrons is to go into these highly directional covalent bonds, right? That happen on an energetically very low level, right? So only way to stabilize electrons further are highly directed bonding orbitals. Okay, by contrast, the metallic bond, the picture is quite different, and that if I draw the same kind of axis where again I have a zero here, so this is typically for large nuclear charges. Now your potential is much broader, right? Because your z over the distance is the z is much larger, and you have much more electrons, right? So your states, there are much more states, and they also the differences decrease with inversely with n to the 2. But now you have all these electrons which you have to fill, right? And so this gap, the gap to zero, is much smaller. And indeed, it's for the metal, by definition, the gap has become zero, right? So there are many states and electrons in wide potential. Actually, there are so many that the gap to the conduction band, which means states for which the electron is no longer bound to the atom, becomes zero. Okay. So this picture changes, right? Then, so for metals, we have a sea of valence electrons that are spread around the atoms, right? And the atoms are like a perturbation to a sea, right? While so atoms are like a perturbation to, and we call this an electron gas or uniform gas. Versus covalent bonds, which are like bonds are perturbations of free atoms. So you should think of these early elements as having so few electrons to spare that their interactions only happen on a small scale as you compare to the free atom. While for the later elements, really each element has so many electrons, they share them, and there's a sea of electrons, right? So it's very non-directional, right? Non-directional. And this is very directional. So this lack of directionality impacts or determines, contributes a lot to the properties of metals, right? So this is sort of a fundamental picture which we cherish. And if we now in this subsection B discuss the properties of metals, then we can see that metals are not brittle, right? But rather ductile. Okay. So this non-directional binding results in very low curvatures. So the potential is rather shallow, and so they are quite soft. So this is great for handling. And in particular, you can see this, that the melting temperature typically ranges between minus 40 degrees Celsius and up to 3,400. And this would be for mercury or for tungsten. And in boiling, you would have to go up to 357 degrees Celsius for mercury and to 5,700 for tungsten. So this boiling temperature means that these are not volatile. Right? In ambient conditions, you would have the probability for evaporating spontaneously is negligible, and the low melting points imply that shaping, forging, smeltering, all these things which we discussed in the very first lecture on how human civilization has made its way through materials in the various metal ages. This is, of course, the reason for that. These properties have enabled us to do this. Because of the electrons being many and close to the point where they would become conducting, also known as the Fermi level. Because of that, we have high electric conductivity. Which is, of course, why these are very crucial materials also for the development of electricity in the society. And you should always remember that electricity, conducting electrons, by the laws of electromagnetism, they always create a magnetic field. Right? So the electromagnets, as they are very common in society, rely on this, of course. Because the high-lying electronic states because they're so high-lying, this means also that they are not transparent, meaning they interact with the light and they reflect the light, and the shallowness of the non-directional binding that implies that the atomic relaxation, if you start wiggling the atoms due to heat transfer, this atomic relaxation is fast, which means that metals are also good heat conductors. Are there any questions? Not, let me still add that the also because of the lack of directionality, and the availability of stabilization of all electrons in the sea of electrons. This means that it doesn't really matter which metal element you're using. So, in other words, the metallic bonds is quite promiscuous with respect to binding partners element type. In other words, there are many alloys where even many different elements can get mixed without need to change the crystal structure. Okay. Let me conclude that this last point is under active research investigation on what